So, in the first and second modules, we have studied about high voltage DC generation as well as high voltage AC generation. Right. Now, in the third module, we are going to learn about generation of impulse voltages. So, these are the three types of voltages that we apply in high voltage engineering in order to test different equipment like insulators or other power equipment. So, we already covered the two, means high voltage AC and DC. Now we will look into impulse voltages. So I think you are already aware of the impulse voltage, right? In networks or whether it in signal processing and all, you have already seen impulse signal. Similarly here, impulse voltage also means for a very smaller duration of time, a high value of response happens or a high voltage exists. So such a kind of voltage is what we call as impulse voltages. So basically, when we have such an instantaneous response or a response that is happening for a very smaller duration, that happens mainly in switching or let us say, or in the first module we have discussed about over voltages, right? So how over voltages can happen? We have divided it into internal over voltages as well as external over voltages, and in external over voltage we have seen that something called lightning impulse, right, or lightning over voltage. So this is the main cause, or this is where we see an impulse response. This is where we see an impulse response in lightning, and similarly we can also see in internal we can also see the switching over voltage. So there also switching means what? An equipment is suddenly switched. So at that particular instant also you can have a sudden operation, and because of that you can have an impulse response. So these are the two conditions when you will have a lightning impulse voltage. Clear? So now let us see how this lightning impulse voltage will cause an over voltage in our system. So that is what we are going to see. How a lightning impulse can induce voltages on the system. Like let us say we have a tower. Okay, we have a tower like this, and what will be the, you have your handles for what your power line is going like this. Okay, your power line is going like this, and apart from this power lines, you have a wire on the top. This wire is what we call as the ground wire. This wire is called as ground wire, right? So this wire is called as ground wire, and what is the purpose of this? This is used in your system in order to otherwise what will happen if you have lightning? It will directly fall on your power line, which will create a higher voltage in the power line, which is not good for the system. So in order to avoid that, whichever is on the upper side or whichever is on the top, that will get lightning at first, so that it will get grounded through this tower, not through what, not through the live conductor, but through the tower. So that is the purpose of that ground wire. But do you know how much current is flowing? Whenever I say lightning, you have your cloud and you have your ground, or you have your conductor. So between that, how much current is flowing when a lightning is occurring? That current amount is around 100 kilo ampere. How much? It is 100 kilo ampere. So that much current when it is flowing. And let me say, we can assume that our tower, whatever tower we have, the resistance of our tower is around 10 ohms. The resistance of our tower is around 10 ohms. So if I have 100 kilo ampere flowing coming due to the lightning, and it is flowing through this 10 ohm, how much voltage will be generated? How much voltage will be generated? How much? So it is what voltage is, what voltage is given by current into resistance, right? So how much is the current? It is 100 kilo ampere. So 100 into 10 power 3 into what? Into the 10 ohms. So how much it will come? 2 zeros here, 1 zero here. So what? It is around what? 10 power 6 volt. Understood? So around 1 million volt is coming through what? Coming to this tower when you have a 100 kilo ampere and a 10 ohm resistance. So that is how, this is how much, this is what it is equal to around 1000 kilovolt, right? So a 1000 kilovolt is there on the tower. On the tower, 1000 kilovolt is there. At this potential here, you have 1000 kilovolt. So because of that, what will happen is that The tower is at what? The tower is at 1000 kilovolt and your conductor is at a lower potential. Your conductor is at a lower potential. So between the tower and the conductor, you have a flashover can happen, and that is how your impulse voltage exists. Understood? So between the tower, how it will happen? Between the tower and what? And the conductor. Between the tower and conductor, flashover can occur. Understood? Or we can say from the tower to the conductor. Usually how flashover will occur? If a over voltage is there on the line, or due to reasons, between your tower, from conductor to the tower, usually flashover occurs. But whenever lightning is happening, it is the reverse. It happens from what? It happens from the tower to the conductor. So that is the main difference when it comes to lightning, and that is how our lightning impulse will happen between the tower and the conductor. Stop change black rectangle. So whatever now we discussed, the lightning is striking the tower directly. So that is called as direct lightning over. Understood? That is direct lightning strike, you can say. There is another one called as indirect. Okay. Indirect lightning is what is indirect lightning strike? It is quite clear that it is indirect. So in case of indirect, what happens is that you have a cloud. You have a cloud like this, and let us say it is charged like this. Okay. Let us say it is charged like this. Okay. So below that you have your live conductor. In the live conductor, when you have this negative charge over here, let us say a positive charge will be induced on the live conductor. Right? Means whichever is nearby the cloud, or on the cloud, whichever is nearby the conductor, that cloud side, whichever charge is the opposite charge will be induced on what? Induced on the live conductor. So this will be at a high voltage potential. Because of that, what will happen? As you are aware of, a conductor and between the ground. Let us say this is the ground. Okay, a conductor and between the ground, you have air, and because of that, what you have your capacitance. So because this capacitance will get started charging, and that will induce what this all capacitor, or what this is what the ground capacitance CG. So all this capacitance CGs can get charged, and because of that. Means what? Because of the induced voltage on the line, because of that also you can have lightning strike. So here what happens? It is not direct from the cloud to the ground, or from the cloud to the conductor. It is happening due to the induction between these two. So that is why this is called as indirect lightning strike. These are the two ways that normally we have our lightning strikes. Now let us see the characteristics of a lightning over voltage, or the characteristics of a lightning strike, okay, or the lightning impulse voltage. So first we will be seeing what are the characteristics of the lightning impulse voltage. Lightning impulse. Okay, lightning impulse. So the main interesting part is that your lightning impulse voltage, that is aperiodic. Means what? It is not a periodic signal like our sine wave and all. It is aperiodic. Then the second point is that it is non-repetitive, you can say. Means the same kind of impulse voltage, it is not going to occur again and again. So that we have to keep in mind when testing a high voltage equipment. We cannot expect that the exact same kind of impulse voltage is not going to occur again. Okay, so usually you have a threshold. Usually you have a threshold for seeing that. So that is the main two things. One is that it is aperiodic, and it is non-repetitive also. Now, if we take the characteristics, how we identify our impulse voltages, characteristics, mainly it is through three parameters. One is what? One is called as wave front time. I will get you into the definition. Wave front time. Second one is called as the wave tail time. Wave tail time. And the third one is what? The third one is the wave shape. Understood? So using this three, we will be able to say that which kind of impulse voltage we have, and we usually analyze our impulse voltage based on this. Like wavefront time, it usually comes from what, 1.2 microsecond. But as I said, since it is non-repetitive, we have a threshold value of what, plus or minus 30%. In case of what, when it come to wave front time. Okay. Then when you take the wave tail time, similarly you have around what, around 50 microseconds is what the tail time, and that also you give a threshold value of 20%. Means you can have a variation from this up to this, because it is quite a natural phenomena and it is not repetitive in mode. So now let us see the impulse voltage waveform and define these parameters. What wave front time, wave tail time, and what is meant by this wave shape and all. Okay. So now let us define these parameters. So how our lightning impulse voltage will look like? Okay. So this is our time axis, and this is our voltage axis. Okay. How it will look like? It will have, the wave shape is quite like this. Understand? So this is the wave shape of a lightning impulse voltage. Let us mark our origin as this, and there are some points which we take for identifying wave front time and tail time. Okay. So first this is O, and let us mark another point like this. Okay. Let us call this as what? Let us call this as A, and this is what? This is 30%. This is 30%, and we have another point. Let us take it as what? 50%. This is 50%, and another point at 90%, and the last point at 100%. Okay. Of what? Of the voltage. In percentage, if we take 100% of the peak value, 90%, 50%, and 30%. So this is what we will be using for our about defining these parameters. Okay. So the time required, let us mark like this. Okay. These are the time required, and let us mark like this. This is OA. Then what? This will let us call as B, and this as C, and this point, what it means, let us call it as D. This is E, and this is F. This is G, and sorry, not this. This is not me, right? Okay, this is H. Understood. So this way, let us mark all the points. Clear? Now, the interesting part is here is that this 30%, if we take, and this is 90%. This 30 and 90, if we join them together and draw a line, and this I am calling it as O dash. There is an origin at 0 time, and another O dash I am marking it whenever this 30%, 90% curve, if we draw a straight line, let us say it meets the x-axis or the time axis at O dash. So these are the parameters we are going to concentrate on. So what is the need for this O dash? What is the need for this O dash? Because the real origin O, when it comes to experiment, when it comes to experiment, we cannot find out this O value, but we can only find what? We can find O dash only. Because it is a fast occurring process. So because of that, it is hard to find the real origin. Instead, what we will see, once we get a wave shape, we will see the 30% of the maximum value, as well as what, 90% of the maximum value. With that, we will draw a straight line, and wherever it meets the time axis, that we call as what? Our O dash. Understood? That is that we will take as our what I can say origin in our calculations, even though it is not true. So that is the main part, and in that characteristics you can see here after 30 to 90, it is having quite a what, linear characteristics. Then again it exponentially increases like this to the point E or up to 100%, and what, then it will gradually decreases. The increase happens at a higher rate and the decrease happens at a slower rate. That is how your wave shape should look like. That while testing, we will be looking for that shape. That it is exponentially increasing quite faster, but exponentially decaying quite at a gradual rate or at a slower rate. So that is the important part. So O dash, I think you understood. Now let us get into O dash. I think you understood what is meant by the Friend time. Okay. What is meant by the friend time? Friend time is usually what? Usually it is from what? From the 0% to your 100%. But usually what we take is like this. It is the time from let us say O dash F means what? From this O dash place to how much from the peak value or from the peak time. So that is what is meant by the wave friend time. Wave friend time. Wave friend time. Okay.
ఆపేనా చెప్పే
So that is the wave front time. But for your lightning impulse voltage to rise from your zero to what to the peak value, that is what is meant by wave front time. And usually we take it as what? We will take it as O dash to the F value. So let us say in this figure O dash F, that is what represents our wave front time. Okay. So in order to and similarly, what is wave tail time? So another characteristics is what? The wave tail time. So what is wave tail time? It's quite easy. Wave tail time means what? From your origin, from the starting point O, or let us call it as O dash. So from that point to reach the 50% value, not at first. After this exponential increase to reach at what? While decaying to reach at what? To the 50%. So this point, why to reach the point H. So let us call what? Wave or tail time means what? O dash H. That is your wave tail time value. Means to reach what from origin or from O dash to reach the value of 50%. That is how we will determine the wave tail time. Now let us calculate this. Let us see how we usually measure this wave front time. Okay. In order to measure wave front time, let us consider two triangles. One is what? One is this O dash. From O dash it starts. O dash like this. This triangle. O dash EF. This triangle is one. Another triangle is this one. Means for this 30%, let us call it as this. This point, let me mark it as this A. This point, let me mark it as HG or the I. Okay. So this point I E and what the I C and this point let me call it as HI J. Okay, J. So the triangle that we have to concentrate is two. One is what? O dash EF. Triangle O dash EF, that is one triangle. Another triangle is what? ICJ. The triangle ICJ. If you look closer, you can see this is right angle and this is also right angle, and we can assume that these triangles are what? They are similar triangles. So once they are similar triangles, then what we can do? We can write the equation that if we take O dash F means what? This is O dash O F, or that is our what? The wave front time. O dash F. This side divided by what? Similar side, which is that similar side Ij. O dash F divided by Ij will be equal to, then what we will take? This Fe. Fe means what? The whatever be the peak value. So Fe divided by what? Fe divided by this side means for this triangle, this side and this side are similar. So that is JC, right? So Fe divided by JC. Now the interesting part is that Fe means what? Fe means Fe means what? Fe means for 0 to 100%. Whatever be the value, whatever be the peak value. So if we call Fe as what? The 100% of that. And what is JC? JC means what? JC is this height. Means from what? From 30% to 90%. So what will be this length? This will be what? Let us call it will be 60. Right. So 100 by 60 will be given by what? Fe by JC, or we can write it as what? 1 by 6. Right. So 10 by 6. So that is what this value will be given by. We have to find out this O dash F by Ij. We have to find out what? We have to find the wave front time, and that is O dash F. Right. Wave front time is what? O dash of F, and call it as what? TF. That I am calling it as TF. And the time here, one more time part is what? Ij only. Ij means from this to this. This is Ij. Ij means whatever be the time needed to reach the 30%, and at this point, this A point can correspond to ij equal to AB only. Whatever be the time needed to reach up to 30%, and j means what? The time needed to reach the 90%, right? So this T1, this ij I can call it as what? Let me call this ij as T1, and T1 means what? The time required to reach from 30% to 90% of the peak value. The time required to reach for the impulse voltage from what? From 30% to 90% of the peak value. That is given by T1. So in terms of that, we can represent the front time as, already we got 10 by 6 here. So 10 by 6 into what? Into the T1. 10 by 6 into T1. So this is how we usually calculate wave front time. You can ask me why I cannot directly take that part. Because it is quite easy if I start from O dash and all, it is a virtual point. It is quite easier if we start from what? If we start measuring the time from what? From the 30% to 90%, because that is where it will be rightly available. But it is quite hard to find out when it comes to experiment the peak point exactly or from the starting point exactly. So that is why we usually find out this way. What? The wave front time is given by 10 by 6 into T1. So this is the equation for wave front time. Clear?
Board main mark.